In this problem, we're asked to convert an integral that's given to us in rectangular form into one that's represented in spherical coordinates. And because we've got this integral already set up, it turns out that we can extract out these ranges of values in rectangular pretty quickly, noting that y here is going to go from 0 to 3, and then we've got x going between 0 and the root of 9 minus y squared, and then we've got z going from the square root of x squared plus y squared up to the square root of 18 minus x squared minus y squared. So let's write out those ranges of values now. We have 0 less than or equal to y less than or equal to 3, 0 less than or equal to x less than or equal to the square root of 9 minus y squared. And the last one, the z values go between square root x squared plus y squared and the square root of 18 minus x squared minus y squared. So there's our ranges of values. We're also going to need our conversions between rectangular and spherical coordinates, so let's get those set up. There we go. And at this point then we've got to decide where to start tackling this conversion. If we break up our triple integral into an integral from surface to surface first, and then another integral over the region dA, then we can see that these z values here represent the bounds on the surface upper and lower. So it would make sense for us to then try and convert these over to their spherical representation, and maybe then we can recognize what kind of surfaces we're working with. So when we take a look at this first one, we have z equals the square root of x squared plus y squared. And over here on the second one, I have z equals the square root of 18 minus x squared minus y squared. So that's our upper surface. This is our lower surface here. Okay, now subbing in for x, y, and z with our replacements here for spherical coordinates. You can go through the simplification of this. It's just a little bit of algebra. And what results then from this one by our conversion is that phi is equal to pi over 4, which turns out to be a cone. And if you don't see that, well, we can take a quick look at it here. You're fixing phi at an angle of pi over 4, or 45 degrees, down from the z-axis, and then you're independent of rho and theta. So what that means is I can take this pi over 4 angle, rotate it around the y-axis, and create this cone shaped. In fact, the radii can stretch out as far as we want, both positive and negative. So this is how you get a double cone out of this thing. But we're only dealing with the upper half of that cone because we've got just the upper half of our root over here. So that turns out to be a cone. If we go through the conversion process on the other one, then what we would get here, and this is maybe a little easier to see because we end up with z squared equals 18 minus x squared minus y squared, which means that x squared plus y squared plus z squared equals 18. So this is just a sphere. We should recognize that from rectangular coordinates. And the radius there is equal to the square root of 18. So its spherical representation would just be rho equals the square root of 18, or 3 square root 2 in simplified form. So that one we've got now is a sphere. So what's happening here is that you've got this cone down below as the lower surface, and it's being capped on top by a sphere. So taking a quick look at this, again graphically, we can look at the cross-section. I usually recommend writing out a cross-section. Here's the xy plane, and then we've got our cone at pi over 4 coming up this way. And your graph doesn't have to be perfect. It just has to try and get the point across so you can see what's happening. And then you've got a sphere coming in over top of your cone like this. So this represents the upper surface. Cone then is the lower surface. So those are the bounds vertically on this particular solid that we're working with. And the volume that we're interested in integrating over is contained within this. Now again, we know that this is pi over 4 and 0 for phi. So phi, if we're going to fill up this entire space in here, phi is going to have to go from 0 to pi over 4. The rho, the radius, is going to go all the way out and everywhere in between to fill up this space, all the way up to the sphere from 0 out. So rho is going to go from 0 out to the radius of the sphere, which was 3 square root 2. So now we have a range of values for phi and for rho. So 0 less than or equal to phi less than or equal to pi over 4. And we've got rho going from 0 to 3 root 2. So we've got two of our three bounds. We still need to know what the range of values is for theta. So we get that by looking back here at these two requirements. Y has to be between 0 and 3, and the x value has to be bounded between 0 and this root function here. So let's take a look at what that sketches out to. We can take those two things, combine them together, and let's see. If y is going to be bounded between 0 and 3, that means we're looking at the x-axis, and this is the xy plane here, of course. So here's y equals 0, and here's y equals 3. And again, we know x is going to be bounded on the left by 0, which is the y-axis, and on the right by this function, which says that x equals the square root of 9 minus y squared. Now we don't need to convert this to spherical, we just have to recognize that squaring both sides gives us x equals 9 minus y squared, or x squared plus y squared equals 9. So this is a circle of radius 3, particularly the upper half of that. So if we were to sketch in the upper half of that circle of radius 3, this is what it would look like. And again, making sure we're obeying our other bounds, that would put us in this first octant sector of this circle. So that tells us then that theta is going to have to travel through that range. So theta is going to go from 0 to pi over 2. So now I have my third bound that I need to finish out our solid. 0 less than or equal to theta less than or equal to pi over 2. So now we've got it. I've taken the liberty of drawing this out for us just so we can see exactly what this volume looks like. So you can see here, we've got this shape, and it does look like this piece of a cone that's sort of trapped in the first octant. And you can see down the bottom exactly that region that we were talking about that we integrate over, as well as the upper sphere capping in that particular cone. So our original integral was over the function x squared plus y squared plus z squared, so that will also have to get converted to spherical coordinates. So let's start setting this up. I'm going to have our triple integral. X squared plus y squared plus z squared. If you'll remember from our spherical coordinates, there was one more thing that we had that I didn't write down, and that is that x squared plus y squared plus z squared equals rho squared. So this whole inside here in the integrand just turns into rho squared when we convert that over. So we're integrating rho squared. And we're integrating in spherical coordinates, so our dv in spherical coordinates, you'll remember, is rho squared sine phi d rho, d phi, d theta. So we'll bring this down into our integral here. Okay, now that we've got that there, you can see I've also simplified down our integrand. Now it's just a matter of adding on our limits of integration. We found that rho was going to go from 0 to 3 root 2. Phi was going to go from 0 to pi over 4. And theta went from 0 to pi over 2. So there we have our integral successfully converted from rectangular into spherical coordinates. Now, although the problem didn't necessarily ask us to compute the antiderivative here, we might as well work through it just for a little bit of practice. So one thing to note is that we've got constants for all of our limits, and our integral depends on rho and phi. And these are a product of these two functions. There's no mixed or mingling happening between these two variables, which means that we can actually separate this integral into 3 independent integrals. It's kind of a nice little trick. Doesn't always happen, but when it does, it's good. So we can take the integral from 0 to pi over 2 d theta, multiply that times the integral from 0 to pi over 4 of sine phi d phi, and then multiply that times the integral from 0 to 3 root 2 of rho to the 4th d rho. Again, not always going to happen, but when it does happen, that we can separate our integral into 3 independent pieces, then we definitely want to take advantage of it. It's much easier than computing a triple integral. So now we just have these 3 single integrals. The first one is just going to integrate to pi over 2. The second one is going to integrate to minus 1 over root 2 plus 1. And the last one is going to integrate to 972 root 2 over 5. So multiplying all of those together then, we end up with a grand total of, well, let's just say it's some big ugly number.